Hello, my name is Peter Broberg, and I'm a PhD student from Craig's research group at University. And today I want to present some of the work I've been doing so far in my PhD studies, together with my supervisors Broberg and Esben Lindgaard, and also my co-worker Christian Krogh. So my project is concerned with predicting wrinkles that arise during forming of binder-stabilized preforms. So binder-stabilized preforms are stacks of dry unidirectional non-crimp fabric with a polymeric binder between each layer to stabilize the preform and make it easier to handle during manufacturing. And these preforms are used to manufacture composite structures, like for instance wind turbine blades, which is the main focus of my studies. But when they are formed over geometric transitions, like for instance the core material of the sandwich structures of wind turbine blades, wrinkling can occur at these transition edges. And these wrinkles cause a severe reduction of the final strength of the wind turbine blades, so we want to avoid them during manufacturing. And to do this, we have created this simulation model that can simulate the forming process of the preforms. And here you can see an example of a simulation where we form a preform over a transition like the one you saw before. And this model is capable of predicting the wrinkling that occur at the top of the transition. Then it's capable of predicting the transverse shearing that occurs in the middle of this transition. And finally, it's capable of predicting the wrinkling that occurs in the bottom of this transition. So for the rest of this presentation, I will talk a little bit more about the background of this project. Then I'll talk about the modeling strategy we have used for this preform model. And then finally, I will discuss the results we have obtained from this model. So let's start with the background for this project. So this project is a part of the MADEBLADES project, which is made in collaboration with LM Wind Power, AB Inventic, and DTU Wind Energy. And the overall aim of this project is to achieve a 30% reduction of the cost of produced wind turbine blades by using these fiber preform materials. And the reason why we want to use these preform materials in wind turbine blade manufacturing is that wind turbine blades have traditionally been manufactured by individually placing these non-crimp fabrics in the wind turbine blade mold, and this leads to very long processing times, especially as the wind turbine blades are increasing in length and some are even exceeding 100 meters by now. When we use preforms to manufacture wind turbine blades, the manufacturing is divided into several steps. The first step is to manufacture the preform in a separate preform tray. Then this preform is pre-consolidated, and after that it is placed into the main wind turbine blade mold. And finally, the whole wind turbine blade is infused with resin and then demolded. So by separating this process of manufacturing the preform and placing it into the wind turbine blade, we can increase the degree of automatization in the wind turbine blade process and thereby reduce the processing times. But as I mentioned in the beginning, one of the challenges we face with this kind of manufacturing is that wrinkling can occur when we place this pre-consolidated preform into the main wind turbine blade mold. So to understand why wrinkling occur when we form this preform, we can consider this very simplified model of the preform. So just prior to forming, the preform is loaded like a cantilevered beam, as you can see up here. And that means that the top of the preform will be in tension and the bottom will be in compression due to the bending moment. And we'll also have shear stresses due to the transverse shear forces. If we look at the non-crimp fabrics that are placed on the compressive side of this preform, then they will have some compressive forces on them from the bending moment, and they'll have some transverse shear stresses that are transferred from neighboring non-crimp fabrics. And as these non-crimp fabrics have a very high tensile stiffness, it's more likely that they will either buckle due to this compressive forces or slide due to the shear stresses here. And that means that the two competing mechanisms in this forming problem is fiber sliding and fiber buckling. So if the forming is dominated by buckling, then we'll have a case like the one shown down here, where we have these wrinkles at the transition edges, and we'll have almost no shearing of the preform, or transverse shearing of the preform. On the other hand, if we have forming that is dominated by fiber sliding, we'll have the case shown over here, where we have almost no wrinkling, and we'll have the preform shearing with an angle approximately equal to the angle of the transition. And of course, during forming of these preforms, we want to have this sliding dominated forming where no wrinkles occur. Based on this simple example, we can conclude that the important deformation mechanism that we need to represent in this forming case is the bending of the non-crimp fabrics to describe the wrinkling and fiber instabilities. Then is the transverse shearing of the preform to describe fiber sliding. And finally, it is the decohesion of the binder material to describe the onset of fiber wrinkling. So now we have defined these three important deformation mechanisms that we need to represent in our model. And now I'll go on to discuss how we have actually implemented it in our model. So the overall modeling strategy we have used for this preform is a ply-by-ply microscale modeling approach. And what that means is that we model each individual non-crimp fabric separately, and then we model the binder interface between each non-crimp fabric as a homogeneous interface. And the reason why we want to do this ply-by-ply modeling approach is that we want to get information on the mechanics going on between the non-crimp fabric plies in the interface. The current model is a 2D model made in the 1-3 plane of the preform, shown over here. That means that the model can describe the following deformation modes, and can describe in-plane extension and compression of the non-crimp fabric. Then it can describe the out-of-plane bending, transverse shearing, and compaction of the non-crimp fabric. And finally, it can describe the separation and the sliding between these non-crimp fabrics. And the two challenges that we face in this model is that, first of all, the membrane stiffness and the bending stiffness of these non-crimp fabrics should be decoupled in order to accurately describe this fibrous nature of the non-crimp fabric. And then the other challenge is that we need to describe this binder interface in a proper way. So in this slide, I will talk a little bit more on how we have solved these two challenges. So the non-crimp fabric is modeled with continuum shell elements in Abacus with the linear elastic material properties. And then we have modeled the non-crimp fabric with this equivalent 3-layer laminate layup to decouple the bending and membrane stiffness. And in this layup we have a stiff and thin middle layer, which is used to represent the membrane stiffness of the fabric. And then we have these two compliant outer layers that is used to represent the bending stiffness of the fabric. And the cohesive interface is modeled as a mixed mode bilinear traction separation law, as you can see down here. And to model this fiber sliding that occurs on the transverse shearing of the preform, this is modeled by this initial linear elastic stiffness of the traction separation law. And this model is solved using abacus explicit. So as input to the model, we have performed 3 characterization experiments. The first one is a cantilever bending test to characterize the bending stiffness of the non-crimp fabric. Then we have carried out a T-peel test to characterize the binder toughness of the toughness of the binder interface. And then we have carried out a transverse shear test to characterize the transverse shear stiffness of this preform. So from this cantilever bending test, we have obtained this observed this nonlinear response of the non-crimp fabric, where we have a high bending stiffness at low curvatures, and then a lower bending stiffness at higher curvatures. And as we use linear elastic material properties in the model, we have also estimated a constant bending stiffness based on Pierce formula, as you can see here, and inputted that into the model. And if you are more interested into this cantilever bending test, I've put some references here for you. So from the T-peel test, we have estimated the mode 1 critical energy release rate of the binder. And we have estimated that from the force that is needed to pull 2 non-crimp fabrics with a binder interface apart from each other. And finally, from the transverse shear test, we obtained this also nonlinear behavior of the preform. And as input to the linear model, we have used this initial stiffness of this response. Yes, so let's now discuss the results that we have obtained. So to compare with the model, we have carried out some vacuum experiments where we had taken a full thickness preform specimen and then placed it on top of a geometry, which in this case is a wedge, and then applied vacuum, and after that visually observed what effects are going on during this forming process. And we observed that at the top of this transition we have a wrinkle in the preform that faces towards the mold, as you can see here. Then in the middle of the preform we have transverse shearing, and at the bottom of the preform we have a wrinkle that faces towards the back side here. So if we again return to this comparison of the model with the experiments, we can see that the model is capable of predicting the location and the overall shape of these wrinkles, both at the top and the bottom transition. And then it's also capable of predicting the delamination, which is the red areas here, binder delamination at the wrinkle sites, which is also what we observe in the experiments. The wrinkles that are being predicted by the model are slightly larger than the ones that we observe in the experiments. And the reason for that is that we use, first of all, a linear bending stiffness, which overpredicts the bending stiffness at the high curvatures, which we have in this wrinkle here, for instance. And the other reason is that we also use a linear transverse shear stiffness, which also overpredicts the shear, the shearing at higher shear angles. Other than that, the model is also capable of representing this transverse shearing going on, and it's capable of predicting that there'll be no delamination of the binder at these shearing sites, which is the same as we observe in the experiments. So now I will conclude this presentation. So this project is concerned with predicting wrinkles that arise during forming of binder stabilized preforms. And the reason why I want to predict these wrinkles is that they cause a severe reduction of the strength of wind turbine blades. And these wrinkles occur at these geometric transitions when a preform is formed at the edges of these geometric transitions. And we have proposed this macro-scale preform model in which the non-crim fabrics have been modeled separately with a cohesive interface between each layer to represent the binder. And this model is capable of predicting the wrinkle location and shape, and also binder delamination at the wrinkle sites. So that was all for my presentation. As I mentioned in the beginning, I'm a part of the CRACS research group, which currently consists of the team and the members you can see over here. So if you're interested in our work or want to collaborate, then don't hesitate to contact us. So thank you for your attention.